This is the second video in our calculation of the pH curve for the titration of a weak acid with a strong base. Right? We are titrating acetic acid, which is a weak acid, with sodium hydroxide, which is a strong base. And in the prior video, we have looked at 2 points in that titration. The initial point, where there's only weak acid, and then the equivalence point, where you have equivalent amount of the acid and the base, and then the pH there is governed by the acid-base properties of the conjugate base. Okay, so that is actually the work that we have here that corresponds to that equivalent point, where again the idea here is that you have acetate in solution, and then acetate can undergo a base equilibrium to turn the pH a little basic. Okay, great. This video starts there in that point, but we go a little bit over the equivalence point. So we add half ml of base more than the equivalence point. And the question is, what is the pH when you add that extra little bit of base to the reaction medium? Right, so we go back to our stoichiometric calculations right here, and then those are the moles before reaction, those are the moles after reaction. Notice that that is the moles when you have 20 mLs of sodium hydroxide, but if you add 20.5 mLs, now the number of moles will be 2.05 10 to the minus 3. And what that means now is that your reaction is not purely stoichiometric. Acetic acid is the limiting reagent, and then you have sodium hydroxide in excess, and the amount of excess that you have is 5 10 to the minus 5 moles. That is the amount of base that you have left. It's just a tiny little amount. Okay? At the same time, you're also producing sodium acetate, which is also has base properties. So here you have to make a decision. What is more important? The contribution of the hydroxide that is unreacted, or the contribution to the pH of the acetate, which is a base and can undergo this type of chemistry? It turns out that without a doubt, the strong base, the hydroxide, is going to control fully what happens to the pH of the solution. The contribution of the acetate, of the conjugate base, is going to be negligible, because that constant is very tiny for the acetate, right? The base constant K/B is 5.6 10 to the minus 10, right? So what that means is that actually acetate does not generate very many hydroxides, or very much hydroxide in solution. Most of the pH, or for us effectively all of the pH, is going to be controlled by simply the excess of sodium hydroxide you have, however small it is. Right? So we're going to completely neglect the acetate contribution, and then what that means is that then the calculation that we have right here is fairly straightforward, because sodium hydroxide is a strong base, and we know how to calculate the pH of a strong base. So let's just carry it on for the purpose of illustration here. And notice that we have to calculate here the concentration of hydroxide, and that is simply the moles that you have divided over the volume. The moles is 5.0 10 to the minus 5 moles, and then the volume will be 20 mLs that you have of the initial solution of the weak acid, plus what you have added, which is 20.50, that will be 0.04050 liters. Okay? So from here you can get to the concentration of hydroxide, which is 1.2 10 to the minus 3 molar. And from there you can calculate the pOH simply by taking the minus based on logarithm of that number, and then you get that this number will be 2.92, and this means that the pH will be 14 minus that, which is 11.08. Okay, this is a very interesting result. Notice that we only have added half ml of the base, and the pH has grown by more than 2 pH units. That's a 100-fold increase in the concentration of hydroxide with only half ml of the base. This makes perfect sense because you're past the equivalence point, right? There's no acid left, right? So everything that you're adding is essentially base, and that is just going to make the pH basic very, very quickly. Right, so when we go to the titration curve, which is going to have this shape, pH as a function of volume. If this is the equivalence point, where the pH will be a little basic, 8.72, we're clearly in the fast rise section on the curve, right? We had a little bit of volume and the pH increases dramatically. Okay? All right, so that's the third point that we have in our titration curve. And we're going to wrap up this video by taking a look at what happens in between the start of the titration, where you only have weak acid, and then the equivalence point. Okay, so what happens when you add only 10 mils of the base? This is a very interesting point, which is very easy to calculate, as it turns out. Okay, notice that at that particular point, what you will have is the following. So you start with 2 millimoles of acid, and then you're adding 10 mils multiplied by 0.1 molar. The amount of base that you're adding is 1.00 10 to the minus 3. Right? So what that means is that the limiting reagent is sodium hydroxide, and you have hydrochloric acid in excess. And initially you don't have any acetate. Okay, great. So that means that at the end of the reaction, the limiting reagent will be completely exhausted, and then you have 1.00 10 to the minus 3 moles of the acid left over, and you also have generated 1.00 10 to the minus 3 mole of the conjugate base. And that is of significance because now you actually have that there are equal concentrations of a weak acid and a conjugate base. And when that happens and the concentrations are reasonably high, we get to something that is called a buffer. And it turns out that the pH calculation for a buffer is very simple using the Henderson-Hasselbalch equation. Okay, so let's repeat that again. Notice that when you add this volume, that is exactly half equivalent of the acid that you have. And what that means is that your acid goes by to half of its original value, and you're generating that half into the conjugate base. So in the end, you're going to have the same amount of weak acid as you have a conjugate base, which is your textbook definition of what a buffer is. And again, as we have seen in prior videos, calculating the pH of a buffer solution is quite straightforward from the Henderson-Hasselbalch equation. All right, so let's see how we do that. Remember that the Henderson-Hasselbalch equation tells you that the pH of a buffer solution when you have a weak acid and its conjugate base is just the pK sub A plus the base logarithm of the concentration of the conjugate base, in this case acetate, which I'm writing as A minus, over acetic acid, which I'm writing as HA. Okay? Notice that the moles of this weak acid and the conjugate base are the same, and because they are in the same volume, then the molar concentrations will also be the same. Right? So what that means is that the ratio of the concentrations will be 1, and the base logarithm of 1 happens to be 0. So for this particular case, the half equivalence point, then the calculation is straightforward. The pH is just the pK sub A of the weak acid, which we can calculate directly from the Aquarian constant, and that happens to be 4.74. Okay, so that is our last point in the diagram right here, 4.74, which again gives us a pretty good idea of how that titration curve looks like for acetic acid being titrated with sodium hydroxide. Now, for the sake of completeness, we can actually then go to infinite base, what will be the asymptotic limit of the titration, right? And notice that when we have infinite base, what you can then think is that essentially all of it is base, and then the pH of the solution will be the pH of the base, right? Notice that it's 0.1 molar concentration of strong base. That means that the pOH is 1, and the pH will be 13, right? So the highest pH that you will ever see will be 13. Okay, and that now completes our titration curve. Right, so in this second video we have seen how to calculate 2 points that are very important in the titration curve of a weak acid with a strong base. We have looked at what happens right after the equivalence point, where just any addition of base past the equivalent point quickly makes the pH very basic. And then we have also looked at what happens when you are at half of the equivalence point. This is kind of a magic situation, a magic point where you actually have that the Henderson-Hasselbalch equation applies fully, and you're actually in the simplest case of the Henderson-Hasselbalch equation where the pH is equal to the pK sub A of the weak acid, and that makes the calculation of the pH straightforward.